Non-covalent interaction is the common name for interactions, the formation of which doesn't result in the sharing of the electron density. Due to their prevalence compared with commonly much stronger covalent bonds, non-covalent interactions play a fundamental role in most physical and chemical processes. Separate branches occupied by electrostatic interactions, which occupied an intermediate position in strength between van der Waals forces and covalent bonds. A special class of electrostatic interactions is attributed to sigma hole interactions, and we have probably heard about many of them. Pnictogen bond, chalcogen bond, halogen bond, etc. There are many names of interactions depending on the type of atom from the group this interaction is formed. The modern classification of the types of non-covalent interactions is very complicated. And as you can see, it implies the assignment of types of interactions to certain groups of the periodic system. Now let me focus on the one non-covalent interactions, sigma hole interactions, halogen bond. Halogen bond is formed by electron donors, which can be presented by molecule signs or individual atoms. Halogens, oxygen, sulfur, selenium, nitrogen, and so on. Halogen containing primarily chlorine, bromine, iodine atoms and ions and molecules. Generally, the covalently bound electronegative halogen atoms can be able to act as electron acceptors due to the anisotropic distribution of the actual symmetrical electron density around them. There are two distinct regions: the region of increased electron density, nucleophilic site located perpendicular to the molecule and corresponding to negative values of electrostatic potential. The region of decreased electron density, electrophilic site, located along the covalent bond, the so-called sigma hole, which acts as electron acceptor in halogen bonds. When halogen bond is formed, the distance between two interaction atoms becomes smaller than the sum of their van der Waals radii. For example, the oxygen-bromine halogen bond length can be between 60 and 95% in the sum of their van der Waals radii. Halogen bonds can be quite strong. For instance, an energy of order of 115 kilojoules per mole is characteristic to triiodide ion. Halogen bond is actively studied because it is one of the most abundant non-covalent interactions in nature, which is present in solids, in liquids and solutions, and in the gas phase. Let me show you interesting examples of the key role influence of halogen bond in the structural and physicochemical properties of substances. The authors of this work reported the gas phase association of polar protic solvent molecule acetonitrile with benzene, halogenated benzene cations radicals using mass electromobility technique and density functional theory calculations. The electrostatic surfaces of the energy structures of the complexes clearly show the formation of ionic halogen bonds, driven by positively charged sigma holes along the carbon-bromine and carbon-iodine bond axis. The authors of this work used ab initio density molecular dynamics to study the fluctuations of hydrogen and halogen bonds in hydrogen fluoride solutions in tetrachloromethane. As could be seen from the snapshot, the solvaceous shell of FHF anion contains a small number of solvent molecules, many of which form non-covalent interactions with fluorine atoms. There could be 2, 3, or even more solvent molecules interacting simultaneously with a total of 6 lone pairs of this anion. Finally, the authors of this work managed to stabilize the high sensitively and explosively diacetone diperoxide and triiodotrinitropbenzene molecules during co-crystallization by forming non-covalent interactions between peroxide oxygen atoms and benzene iodine atoms, with forming the infinite chains. Despite wide abundance of halogen bonds, the relation between halogen bond and its electronic structure parameters, which are related to the halogen bond strength and geometry, aren't yet fully understood. In Baylor's quantum theory of atoms and molecules, the presence of halogen bond could be detected the bond path which follows the reach of maximum electron density between the halogen and electron donating atom. Along the bond path, both the electron density and electrostatic potential go through minima. Just a couple of years ago, an electronic criterion has been established, according to which when the halogen bond is formed, the electron density minima is closer to the halogen donor, while the electrostatic potential minima is closer to the electron donating oxygen atom. And the distance between these two minima seems to be sensitive to the electronic structure of interaction moieties. Moreover, when the electron is donated by the oxygen atom of a PO group, the halogen bond formation and the corresponding electron density redistribution should cause the change of the phosphorus 31 chemical shift. Thus, the aim of our work was to examine the correlation between chemical shift and the halogen bond energy, length, strength, and the distance between these two minima. In order to achieve this aim, we have considered by quantum chemical calculations 128 complexes formed by the same electron donor, trimethyl phosphine oxide, and various halogen donors. For each complex, we have considered, in particular, the calculated, in particular, the complexation energy, delta E, the distance between ED and ESP minima, delta R, and the change of the isotopic value of the phosphorus 31 and nuclear shift upon complexation, delta P. The halogen-containing molecules include compounds involving halogen atoms from fluorine to astatine. These are simple halogens, interhalides, halogenated methanes, ethylenes, and acetylenes, sulfur-containing molecules, various organic and inorganic compounds with various electron donor and electron acceptor groups. Now let me turn to the most important dependencies obtained, which for simplicity I will consider on bromine-containing complexes. As can be seen, the complexation energy, which, as I said, determines the strength of the complexes, decreases rapidly with increasing the distance between interacting atoms. For instance, for the strongest bromine-containing complex with the complexation energy of 88 kilojoules per mole, the oxygen-bromine distance is 62% of the sum of their event mass radii, whereas for the weakest complex with energy less than 10 kilojoules per mole, the oxygen-bromine distance is close to 90% of sum of their event mass radii. It turns out that the dependence of delta E on delta R has the same character. As the strength of the complexes decreases with increase the distance between ED and ESP minima. This graph also shows the dependencies of the positions of the minima of electron density and electrostatic potential from oxygen atom for corresponding complexes. As can be seen, when the strength of the complexes decreases, the positions of the minima move farther away from oxygen atom, and the distance and their distance from each other increases. Now let's move on to the chemical shift of phosphorus. It's sensitive to all these parameters, to the halogen bond energy, to the halogen oxygen distance, and these two minima. As can be seen, the phosphorus chemical shift changed in a fairly wide range, almost by 15 ppm, when the complex get from weak to strong. Also, the chemical shift of phosphorus could be used as a spectroscopic descriptor of halogen bond electronic structure. It correlates quite well with delta R parameter, and it becomes possible and convenient to solve the inverse spectroscopic problem. From the phosphorus spectra, one can tell how far away the halogen atom, how the electron density is distributed between the oxygen and halogen atoms, and how strong the resultant complex. The scattering of the data points of these dependencies is relatively small. From the correlation line, it's a simple exponential function for both cases. And the precision of these predictions is relatively high too. For example, the average oxygen bromine distance is
2 minutes.
Could be predicted with 4 or 5 hundredths of angstrom. What happens to these dependencies when we consider other halogens? As you can see, the dependencies have the same character, the same story, only the stiffness of the curve changes, which could be related to the increasing the polarizability of the electron shells of halogen atoms from chlorine to iodine. And all these dependencies can be used as descriptors of the halogen bond electronic structure, its energetic and geometric characteristics. In addition, in summary, first of all, dimethyl oxide is a robust and convenient part in the halogen bonds, and phosphorus chemical shift is a sensitive reporter of their structure. The described pathology can be extended to the 2 types of complexes with hydrogen bonds, which my colleague Mikhail Kostin is engaged in, and for complexes with phosphine selenide, the magnetic active nuclei of which is directly involved in the formation of halogen and chalcogen bonds. And it could be expected that the selenide atom nuclei would also be a sensitive reporter of their structure. This work was supported by Russian Science Foundation, and I'm grateful for your attention and ready now to answer your questions. Thank you.
Okay, thank you very much indeed. I have some questions. I have seen in one of your pictures that some shifting in some some shifting in ppm is equal 8,700 exponent minus 2.5 and next R in angstrom. How it possible that the exponent have dimensions in power?
Yeah, I simplified the view of these equations because the parameter in exponential degree
could not have dimensions.
It contains the parameter which forms the dependence with no dimension.
No, but I certainly look. Here you have R in angstroms, right? How is it possible? It should be normalized
2.5 will be dividing the angstrom, but I omitted this in these dependencies just to clear the
is that the conference or
question.
Okay, I didn't understand.
If you cannot.
But anyway, have you any other question, colleagues? Sergey Vasilyev.
May I ask a small question?
Yeah.
Yes,
About slide number 9. You on the left graph have the smallest r squared, but the data seems to be in the same range of errors. So why the r squared for chlorine is smaller than for the others?
Okay. Your answer, please.
These dependencies contain the same number of data points for chlorine, but when we consider this dependence, the scattering is much stronger, and that is, and
on the left graph, I can see if the scatter of the data for chlorine is larger. I think that for bromine, it's
no,
or it's just trickiest thing by eye.
it seems to be so because the horizontal scale is much different from the scale on this one, and that is.
Not so different, by the way. Okay. Okay. Thank you very much indeed.